Okay, today we're going to talk about scatter plots and linear correlation. So understand that we are about to jump into a topic on statistics as it relates to bivariate data. In other words, situations where you have two variables that you're going to compare against each other to see if there's a relationship. And so when we think about two variable data, hopefully when we think about graphs that would represent two variable data, scatter plots come to mind. And scatter plots are not new to you. You have the basics as to what a scatter plot looks like and what it's designed to try and show you. So some of this is going to be review, but then we're also going to jump into this new thing called linear correlation, and this thing called correlation coefficient and what it all means. So we're going to look at this example here, and it says a study examines two new obedience training methods for dogs. The dogs were randomly selected to receive from 5 to 16 hours of training in one of the two training programs. The dogs were assessed using a performance test graded out of 20. So I don't know if you know anything about dog training or anything like that. By the way, there's a little puppy. If that doesn't warm your heart, then you have no soul. Dog training methods, I think, greatly vary. I myself have never experienced or been witness to a dog training method. I've only seen what I've seen in movies or TV shows as to how dog training works. But we have these two methods we're going to compare. The one is called Rogers method. The other is called Lang system. And so what has happened here is some data has been collected from some dogs that have taken either of these two training systems or methods. And so you can see there were 10 dogs that were that had some data recorded for Rogers method. So for example, this first row in the Rogers method table here simply says that the dog received 10 hours of training, and at the end they got a score of 12 out of 20. Moving over, say, to this Lang system table, this row right here says that this dog received 16 hours of training and scored a 7 out of 20. So in trying to judge which of these two training methods is more effective, it's totally natural to look at the tables of data and try to do the eyeballs test and get an idea as to which one we think is more effective. But understand that's really limited, and we're also looking at two tables where there's 10 rows in each. And perhaps that's not realistic as we think about larger sets of data and how our eyeballs test might be, very, very limited to only very obvious cases. And maybe this right here is an example of an obvious case, but we're going to move forward and get into the actual math to show how maybe, in an obvious case, our eyeballs are looking at something and our brain is forming some kinds of opinions that may in fact be related to the math that actually connects to them. So in terms of a strategy for trying to figure out which one is better, yes, the eyeballs test. Good. Done. Moving on, I think the next thing would be is to probably make a scatter plot. A scatter plot could give us a very quick visual as to which training method looks more effective. If we were to make a scatter plot for each of these, we would put hours of training down here horizontally on the x-axis, and the score would go vertically. And that's simply because here we're trying to test to see if the hours of training affects score. Okay, so we would put hours here, and we would put score over here. As I try to write sideways, it's not exactly easy to do. Not bad. Again, because we're trying to test to see if hours affects score. So independent variable goes here, dependent variable goes here. Hey, that shouldn't be new, but I guess it's worth stating. So I've gone ahead and already made the scatter plots for each. And let me see here, Lang system's not showing up very well. My screen formatting size is just a little different on this machine. Here, let me just fix this a bit. Shrink that down. Come on in here, Lang system. Okay, that's pretty good. Oh, I lost the title. Get in there. All right. So here we are. So the eyeballs test now is really proving to be something, because as we look at the Rogers method scatter plot, I hope the clear message is the hours of training does seem to affect the score of the dogs, and that for the Lang system it seems very less certain that the hours of training has either a positive impact on the score, a negative impact on the score, or any impact whatsoever on the score. So it certainly looks like the Rogers method is proving to be more effective. And in this obvious case, I suppose we could be done with this problem right here. But what if it wasn't so obvious? What if the Lang system data was quite comparable to the Rogers method, and we really, really wanted to know which one is truly better? Well, this is where we get into some math, and this is called the correlation coefficient. Okay, so to understand correlation coefficient, understand there's this big fancy formula, okay? And this big fancy formula that you see here looks daunting, it looks intimidating. It's not really. We're going to go through an example of how to use this formula, and we're going to see it's very methodical in terms of how we can make sure that we evaluate the correlation coefficient correctly using this formula. But we have to have some idea of the kinds of numbers we're going to get from this formula, so that by the time we jump into some actual number crunching, we kind of know where it's going. So when we do any set of data into this formula, we are going to get a score between -1 and +1 every single time. Okay? If you don't get a value between -1 and +1, rest assured you have a mistake. And you'll have to go back and try and identify where that mistake is, because you will always get a score between -1 and +1. If you get a score of -1, that means your data has a perfect negative linear correlation. And if you have a score of +1, then your data is showing a perfect positive linear correlation. And you can see there are different sort of benchmarks along the way to define weak versus moderate versus strong. Positive values from this formula indicate positive correlation, and negative values indicate negative correlation. Taking a step back, let's just make sure we know what some of these words mean. So I've got some scatter plots here, and we're just going to quickly go through each one and give it the, I guess, correct descriptors as to what this data is showing. This first scatter plot, no doubt it's showing positive, but is it showing strong, perfect, moderate, weak? Well, this is where it becomes a little bit subjective when we don't necessarily have some sort of exact sort of like numerical data to kind of lean on. And of course, that's where this correlation coefficient formula and the value we get from it really shows how great it is. But this first one here, I guess we would probably call it strong positive correlation. Strong positive. The second one here, this looks like perfect negative correlation, and those are the words we would use there. This third one, boy, it certainly looks like no correlation. It doesn't look like there's any connection between whatever variable x is and variable y. Moving down to D, we get into some sort of wishy-washy ones here. So is D showing a weak positive correlation or moderate positive correlation? It's a little bit subjective at this point as to what you might say versus maybe somebody else. Same thing with E. Is this moderate or weak positive correlation? Somewhat uncertain. And finally, this last one, F, also a little bit subjective. Is it showing strong negative correlation or moderate negative correlation? Kind of hard to tell. And again, that's what this correlation coefficient formula is all about. So let's get into it. Let's actually do this for the Rogers method and the Lang system, and we'll show how the number crunching goes. So what is it that we're going to be doing with this table of data, and how does it relate to this formula? Well, as we look at the formula, there's some things to, I guess, notice. First of all, some new symbols, right? And I shouldn't say new symbols, but symbols that perhaps you're not still super familiar with. For example, this symbol right here, right? This means the sum of, all right? So right now the formula is saying n, which is the number of, I guess, sets of data that you have. And for Rogers and for Lang, it's both 10 sets of data. So n is going to be 10. But this says the sum of x times y. So you can see we're going to need to do x times y and then find the sum of it. Here this says the sum of x, the sum of y. Here on the bottom of the formula, you can see we're trying to here find the sum of x squared. We have to find the sum of x, but then square it. And then similarly, we have to find the sum of y squared, and then finally the sum of y, and then square it. This is coaching us or giving us hints as to what are additional things we have to do with this table. Because we are asked to find the sum of x squared, does it make sense that we are going to have to find the sum of column x? And by the way, x is the hours, okay? X is the thing that is being plotted horizontally on a scatter plot. And remember, let me just back up here to this slide. We're putting hours horizontally and score vertically. Hours is the x, score is the y. So in this formula, when it says find the sum of x, all we have to do is find the sum of this first column right here. This is the x. And when it says find the sum of y, got it, no problem. Now also in that formula, and perhaps it would be good if I copied and pasted this now into this slide so we can see it without having to flip back and forth all the time. Let me just shrink it down. Okay, let me just stuff it over here. We have to find the sum of xy. And so hopefully it makes sense to you that that means we would need to have and I'm trying not to show you everything here. I'll just do this. We would have to find the sum of, or pardon me, yes, find the sum of x times y, which means we would need all the x times y's. Also looking at the formula, we need to find the sum of x squared. So hopefully it makes sense. We're going to need to determine the x squareds for every single row. And then finally, we have to find the sum of y squared. And so hopefully, again, that it makes sense that we would have to then find the y squareds and then add them up. So just looking at this first row, because I want you to know, it's as much as this is tedious, it's not that hard. These are the values, x and y, that were given to us in our table of data, right here, x and y. Okay, so x times y, well, 10 times 12, 120, easy. X squared, what's 10 squared? 100. And finally, what is 12 squared? 144. And you simply repeat that process all the way down your table, okay? And the whole point of doing this long table is to get the sums. So the sum of x is 91. The sum of y is 114. And the sum of xy is 1254. The sum of x squared is 1027. And finally, the sum of y squared is 1548. Okay, now that we have those, we are able to use the formula, and I'm just going to bring it down here now and extend the page a little bit. We're now ready to use this formula. We're now ready to input these 5 orange numbers, if I can call them that, these orange numbers into this formula. And it just becomes a BEDMAS problem. So as I get started here, and I'm going to try and go through this rather quickly, we have 10 times, okay, the sum of xy is 1254, minus 91, that's the sum of x, times 114, that's the sum of y. All right, divided by big square root. All right, so in here it's now 10 times, okay, the sum of x squared, that's 1027, minus the sum of x, 91, squared. Close that bracket, and a new bracket. My watermark is kind of in the way, so I'm just going to move up a little bit. But I need those orange numbers to look at. There we go. Okay. So then over here we have, hang on, 10 times, okay, the sum of y squared is 1548 minus the sum of y, 114 squared. Okay, and when you get using your calculator and doing a whole bunch of bed mass, order of operations stuff, you end up with 0.961. I had to grab my calculator and punch it all through myself. Now, I don't recommend trying to do this all in one step on your calculator. By all means, take as many steps as you need to get to this. So 0.961, what does that mean? Well, let's reflect back on this spectrum here. 0.961 shows that it is strong positive correlation. And that also corresponds to the look of the scatter plot. If I go back here, this Rogers method certainly looks like strong positive correlation. Now, could we have looked at this and went, oh, it looks like 0.961? Of course not. And that's the whole point of doing the number crunching. In a similar way, if we do all of the work for the Lang system, and it's, when I say all the work, we do all the same steps, okay? And then we find those sums, which are here, and then we go and use the correlation coefficient formula and plug in all the numbers for Lang's system, we end up with, and I do believe I have this right, hang on a quick moment, let me just verify my number. We end up getting negative 0.224. Now, what does that number mean? Well, looking back at the spectrum here, negative 0.224 shows that there is a weak negative correlation. And then if you look at the scatter plot for Lang's system, you'll see that not only did it look sort of wonky to begin with, but that there's actually a negative correlation taking place here. Now, the correlation coefficient doesn't talk about the steepness of the line. It simply talks about how closely the data comes to modeling a line, okay? And as you can see here, when I put a line of best fit very quickly on the Rogers method scatter plot, those dots collectively are pretty close to that line. They vary some, but they're pretty tightly, connected to that line. Lang's system, not so much. The dots are very loosely scattered. They have a lot of distance between the dot itself and the line. And as much as that might be the correct slope of the line, the dots just don't fit it very well. And there's that negative 0.224 value sort of, and what it looks like on a scatter plot. So what, of course, this means overall about Rogers' method and Lang's system is we would, at this point, make a conclusion that based on the data, we would say that the Rogers method is more effective than the Lang system. In fact, we might even argue it's not even close. Now, without delving into future topics, it's also natural for you as a critical thinker to think to yourself that there's other variables to consider here than just hours of training and score. Things like the types of dogs that were perhaps evaluated. What was the entry score in terms of obedience for each dog versus their exit score? There's just a lot of factors here that are not being considered in this very simple example. But that's the beauty of statistics, is you can grab a couple sets of numbers, do some sort of analysis, form a conclusion, and your conclusion may or may not have enough validity to it to actually be something that you would be willing to, commit to or to publish in an article of some kind. So overall, that is how correlation coefficient and scatter plots connect together.